What we're looking at here is simplifying radical expressions. And I have the square root of 75. Nothing's coming to my mind right now that times itself makes 75. But maybe what I can do is kind of work backwards. Remember what we did last lesson? We kind of took two separate radicals and made it one radical. What if there's a way to take one radical and make it two radicals? It's kind of funny too. Two radical? Two, okay. So let's think about, since this is a square root, the square root of 75, I want to make something times something equals 75. 70 times 1 does it. 15 times, let's see, 1, 2, 3, 4, 5. 15 times 5 does it. But there's also a 25 in there. 25 times a 3. And I like that 25 because, one, it's a big number, but it's also a perfect square. And that's the key to solving these problems, or looking for what's the largest perfect square I can find that's a factor of my original number. All that being said is, what's the largest square, perfect square, that's a factor of 75? 25 is. So I separated them out in one radical. I can break them out to their individual radicals. Anybody know what the square root of 25 is? So there I went, or there I go. Square root of 75 simplified is 5 root 3. And 5 root 3 is simplified. There's no way that I can break root 3 down any farther, but there was a way I could break 75 down any farther as a root form. Let's look at another example. The cube root of 54. Well, the cube root of 54 itself doesn't do me any good. So I got to think of, how can I factor 54 such that one of the factors is a perfect cube, and the biggest perfect cube that I can think of. So we got to think of what are cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. That's as far as I'm going right now. So which one of those factors did you hear was also a factor of 54? 27. So let's rewrite this then as the cube root of 27 times 2. To make them their own cube roots. Cube root of 27, 3. And then I'm left with a cube root of a 2. So there, that is simplified. 3 cube root of 2 is the same thing as cube root of 54. It's just this one is reduced. Where are you guys going with this one now? The 5th root of 64. Got to think of 5th roots. Yeah. See, 1 to the 5th is 1. 2 to the 5th is 32. 3 to the 5th is a big number. So fortunately, 32 is as far as I need to go. So I'm going to rewrite it as the 5th root of 32 times 2. The 5th root of 32 times the 5th root of 2. And the 5th root of 32 was 2. And I can't do anything with that, so that's the 5th root of 2. So that problem is reduced down as far as it goes. The last example I want to show you, let's throw in some letters, or variables if you want to use a math term on that. So I have the square root of 500 times xy squared. 500 xy squared. Now, let's go ahead and start breaking things down one at a time. So I have to look at the 500, the x, and the y all separately. So can you think of a way to break down the 500 so that one of its factors is a perfect square? 105. The x is just an x, and the y squared, just a y squared. But I can put them all underneath their own radicals now. So I have 100 times the square root of 5 times the square root of x times the square root of y squared. Square root of 100 is a 10. Square root of 5, square root of 5. Boring. Square root of x, square root of x, and the square root of y squared is a y. Let's clean it up a little bit. Let's get the non-radicals out front. So I have a 10, y, and since these have the same index, I can also group them together underneath the same radical too. So I have 10y square root 5x.